Okay, take out your outlines. Let's do this.
Oh.
Let's go.
Oh yeah. Like how the class is just only this side of it.
All right, so we talked quite a bit about London dispersion forces. Even though I wasn't super thrilled with the idea of them in general, but we've got it. That's the best explanation we have. If temporary uneven distribution of electrons in one atom or molecule then induces a temporary dipole in another atom or molecule. It's a very weak force, but weak enough to hold atoms and molecules together. Although remember, the key is bigger the size, the bigger that effect is going to be. The example I gave yesterday. For a nonpolar molecule with strong intermolecular forces. Nobody remembers that. We were all too tired to store that in our memory. A nonpolar molecule with even higher, stronger intermolecular forces than water. Wax. Yes. Right? Because it is composed of molecules, waxes are somewhere in the mid-20s of carbon atoms. So it's like 25 carbon atoms and then a whole bunch of hydrogen atoms on there. It's nonpolar, but it's very, very large. So the dispersion forces, they increase with the contact area. They increase with the size of the molecules because those molecules are more polarizable. Remember the picture I drew yesterday, right? We're trying to maximize attractions and minimize repulsions. So even if we induce just a little positive and a little negatives on either side of that big long molecule, the attractions will be really strong, the repulsions will be really weak. All right, so we're going to talk about some properties today, some of the properties that are dependent on the strength of the intermolecular forces, but I want to just make sure we understand dipole. If a molecule is already polar, if because of the shape it ends up with a negative end and a positive end, then those molecules are going to attract each other, positive end of one molecule to the negative end of the other molecule. Right? All these attractions are positives attracting negatives. Right? So, number 3, that's what it's talking about. And I have a picture on the notes right here. A lot of arrows going on there, but what is this trying to show us?
What parts attract and what parts repel.
Yeah. So obviously there's no way to completely eliminate the repulsions. Okay? What we're trying to do is arrange these molecules so that we can maximize the attractions of the positive and the negative ends, try to keep the like ends as far away as possible. Okay? So they might ask you to draw something like this. And again, we're trying to arrange them by putting the pluses and minuses as close together as you can possibly get them. I think yesterday we talked a little bit about number 4. Dipole-induced dipole interactions, yeah? So if a nonpolar molecule can get a temporary dipole and induce a dipole in another nonpolar molecule, then something that already has polarity, something that already has a positive end and negative end, should definitely be able to induce a dipole in another molecule. Right? Which is part of the reason that if I shake this up, it is possible to get oil and water to mix. Right? They don't instantly fly apart from each other. Okay? The water molecules can induce a little dipole in the oil molecules and then cause an attraction. Why does it separate out? Because the dipole-dipole attraction the water can form with itself is stronger than that dipole-induced interaction. Okay, so eventually because of random motions, a water molecule finds another water molecule, it's going to stick to that and move the oil out of the way. The strength of these forces increases with the magnitude of the dipole on the polar molecule and with the polarizability of the nonpolar molecule. What would be an example of that? Well, I can think of another example of a nonpolar molecule that can dissolve in water. Carbon dioxide. Right? Soda. Well, what happens if I shake soda? It's very easy to get that carbon dioxide to release from the water molecules and come flying out of there, right? Well, I guess CO2 is a gas, whereas oil is a liquid, so it's a little different simulation here, right? But the bigger the nonpolar molecule is, the more it can attract to water. So I would expect that larger nonpolar molecules than CO2 would be able to dissolve in water even better. Right? Smaller nonpolar molecules, like helium, not a molecule, an atom. Helium, I would expect to be very hard to get to dissolve in water. CO2 is much bigger than helium. CO2 doesn't dissolve in water all that well. Right? So if helium's even smaller and nonpolar, I would expect that to be even less soluble in water than CO2 is. All right, but maybe some bigger molecule like propane or something like that, you might be able to get more propane to dissolve in water because, again, the polarizability of the nonpolar molecule. So the size of the nonpolar molecule, the bigger it is, the more polarizable it is, the stronger interactions it should be able to form with water. All right. And then hydrogen bonding, you saw that in that simulation? DNA is probably, well, water and DNA are probably the best examples you'll see of hydrogen bonding. Which is why I put them on the notes. Hydrogen bonding is just a really, really strong dipole-dipole force. It's still the partial positive end of a molecule interacting with the partial negative end of another molecule. Okay, but the reason we give it its own sort of special name, hydrogen bonding, is probably because of this graph right here. This graph has a bunch of molecules, and from left to right, the size of the molecules is increasing. So if we look at this dark blue line, as we go from CH4, SiH4, GeH4 to SnH4, the central atom is getting larger and larger, right? But they're all similar, and we can see this is the boiling point on this axis. The boiling point is increasing as well. So as the molecules get slightly bigger, their polarizability gets bigger, and so their intermolecular forces get stronger. Okay. Now we can see that pattern even in polar molecules too, right? HCl versus HBr versus HI. HI has a higher boiling point than HCl. Why? Iodine has a bigger radius, so bigger molecule. But these are polar molecules, right?
They had that little thing where it was like the repulsion was weaker in bigger molecules than it was in smaller ones. So that attraction was stronger.
Maybe. You're saying in HI, if it's a polar molecule, the bigger polar molecule, you can do the same thing I talked about yesterday, where you can make the like charges farther apart in HI than you can in HCl. HCl being smaller, the like charges are going to have to be closer together. That's a possible explanation. What? It is, they are dipole-dipole. They are polar, right?
Yeah.
You probably learned that polar molecules attract by the dipole-dipole interaction. But don't forget, dipole-dipole acts in addition to London dispersion. So even polar molecules still attract by London dispersion forces. So as a polar molecule gets bigger, its London dispersion part of the interaction should get stronger and stronger as well. Okay, so you can compare polar molecules. The temptation usually with polar ones is to think about electronegativity. And to try to say, well, if we're comparing HCl and HBr and HI, maybe it's the fact that they have differences in electronegativity, so maybe one of them has a larger partial positive and partial negative. That would make sense, right? Coulomb's law says the bigger those partial charges are, the stronger the attraction should be, right? But if we look at it, HI is actually the least polar of those three that I talked about, right? HCl has the biggest difference in electronegativity there, right? But HI had the highest boiling point. So the increase here is not because of some difference in how polar the molecules is, it's actually based on the size of the molecule, the polarizability of that molecule. Okay? So yes, electronegativity is important, molecular shape is important to figure out whether we have a polar molecule or a nonpolar molecule. Because in general, polar molecules are going to have stronger attractions than nonpolar molecules, right? The light blue, the green, and the red lines are all polar molecules. All the ones in light blue are bent. All the ones in green are trigonal pyramid. These are all linear because they just have two atoms, okay? But even if things with about the same weight, the nonpolar ones are the weakest and the polar ones are stronger because the dipole-dipole is in addition to London dispersion force, okay? Which is also why you see an increase for all of these graphs. This molecule is bigger than this one, so its London dispersion forces are stronger. Okay? Now, just like we talked about with wax and water, even a nonpolar molecule, if it's big enough, it can have stronger intermolecular forces than a polar molecule. Right? So they're not going to give you a big nonpolar and a small polar molecule and ask you to compare them. They're either going to give you all nonpolar molecules, in which case you'll be able to go by size, or all polar molecules, in which case you'll be able to go by size. Okay? So don't use electronegativity difference when you're explaining intermolecular force. Use the size when you're explaining intermolecular force. Okay? But look at the three on the left. NH3, HF, and H2O. Those are pretty small molecules, and yet they have way higher than expected intermolecular forces. Their boiling points are way higher. If this trend continued here, those things are so small, their boiling point should be down here. The reason they're so high? Hydrogen bonding. That's this term we use, hydrogen bonding, for an unusually strong intermolecular force. And we see that unusually high intermolecular force with elements that have a very high electronegativity. The highest electronegativity nitrogen, oxygen, fluorine. And chlorine's pretty high too, right? Why don't we include chlorine in hydrogen bonding? Well, it's bigger. Maybe that's part of it. Okay. Actually, if you look at HCl here, it's a little bit higher in boiling point than you would expect based on the trend, right? If we sort of follow this trend out, it really should be somewhere down here. It does get a little boost in intermolecular forces, okay? But nowhere near as big of a boost as H2O, HF, and NH3. Okay? For hydrogen bonding, that's what you're looking for. The first thing you have to see is either an NH bond, an OH bond, or an FH bond. If you see that, then this hydrogen can form a hydrogen bond with any other highly electronegative element. It doesn't even have to be in the same molecule. Or with the same type of molecule, I should say, right? So we could have something like this. We don't have an OH bond here, but we already have the NH bond, which is the first thing we need to have hydrogen bonding. We need a hydrogen bonded to one of those three elements, okay? And then this hydrogen, because it has got such a large partial positive charge, it's going to interact with another highly electronegative element, even if that element is not bonded to hydrogen. In this case, it's bonded to carbon, okay? But this is a hydrogen bond. Now we should have seen that in that simulation that we did the other day, because when you look at those bases in DNA, that's what you see. You see an NH here, the thing that it's forming the hydrogen bond with, that dashed line is the hydrogen bond. This nitrogen does not have any hydrogen on it. It's bonded to a carbon here and a carbon here. And yet it's still considered to be a hydrogen bond. If you have that NH and you have some NO or F anywhere else, it can form that hydrogen bond. Here's an NH bond interacting with an oxygen. That oxygen is bonded to a carbon. It's not bonded to another hydrogen. Yet this is still a hydrogen bond. Here's ethanol. The red is oxygen, the white is hydrogen. So we have an OH bond here. Where does the hydrogen bond form? Well, it forms from that hydrogen to some other oxygen in another ethanol molecule. Okay, so there's a hydrogen bond here. All right. Here's another OH. And the hydrogen here is interacting with the oxygen back here to make another hydrogen bond. This dashed line here, it's kind of hard because of this perspective here, but this oxygen is back behind the molecule, and there's a hydrogen coming off of here. You can barely see the little curvature of it here. But it's the hydrogen behind here that's connected to the oxygen that's forming the hydrogen bond with the oxygen over here. Okay? What else? Did they talk about any other biological aspects in that program we did?
Talked about antibodies.
They talked about what?
Antibodies. And,
Antibodies?
yeah.
Yeah, I'm thinking of, there's another couple of big examples. Have you guys heard of alpha helixes? Who's a bio person in here?
That's why he's taking off. That's
Is
why
that
we're-
I'm struggling to chew my gum right now. Stop talking to me about this crazy stuff. All right. Alpha helix, you'll see them in textbooks where they look like this. Very common when you're trying to represent the structure of a protein. So in these proteins, we have all these amino acids, and they're all chained together. But amino acids all have the same sort of backbone. They have something like this, and they have a carbon, and they have have something like this. All right, and coming off this carbon in the middle is a bunch of different carbon chains. A bunch of different structures come off the carbon in the middle to make all the different amino acids. Leucine, isoleucine, valine, proline. It's all different stuff coming off of here, but they all have the same basic backbone here. And what happens is we take the OH here and the H here. This one combines with the OH and another amino acid, right? These combine to form H2O and the amino acids come together. Over here, this OH combines with the hydrogen on the nitrogen of another amino acid on this side. H2O leaves, the rest of the molecule connects, and we make this big long chain of amino acids. But they all sort of have this same base where there's a nitrogen with a hydrogen still sticking off of it, because only this hydrogen got removed, and then you have a carbon with that very electronegative oxygen on it. All right, and they're trying to show that here. The textbooks, they don't want to show something that looks like this because it's just like hard to figure out what the heck that is even showing. So they show this little corkscrew thing. The corkscrew is really that carbon-nitrogen backbone from the amino acids, but the nitrogen-hydrogen bond here creates a hydrogen bond with one of the oxygens further down the chain. Back here, there's another nitrogen-hydrogen here on one of the amino acids. It's forming a hydrogen bond, again, with the oxygen on some other amino acid further up that chain. And basically what those hydrogen bonds do is to keep the carbon backbone of the protein in sort of a spiraling configuration. It's called an alpha helix. It's one of the major structures when we're talking about the shapes of proteins. Another major one are beta sheets. See if I can find a good picture of it. Did find one, but apparently everybody's streaming the Cubs rally and you have no bandwidth. Or I picked a bad website. Yeah, bad website. Okay. So another thing that can happen is instead of this thing coiling up and forming that little corkscrew, that alpha helix, another thing is one big long chain can come up next to another big long chain, and here's your NH bond. That NH bond, the hydrogen, forms a hydrogen bond with the oxygen here. And here's an NH from another amino acid in the other chain. It's forming a hydrogen bond with the oxygen here. Hydrogen bond here, hydrogen bond here, hydrogen bond here. So you get this regular pattern of hydrogen bonds that keeps those long strings of amino acids sort of in this kind of flat configuration. They're just lined up next to each other. Now this end of the chain, it could do all kinds of stuff. It could go do an alpha helix or some other thing and then come back, right? And another chain and another chain right there. So we don't know what's on the other side of these, but it's possible to get a whole bunch of these things to line up in this way that we call a beta sheet. It's not completely flat. They've got a side view here. Because those carbons here are, let's see, what's the hybridization here? What's the shape? sp2 is the hybridization. What's the shape? No. There's 3 atoms and no lone pairs. Trigonal planar, right? So there's sort of that, you get those shapes memorized, right? So you've got some trigonal planars here. This thing's going to be, well, this one's going to have a lone pair on it, so that's going to be trigonal pyramid, okay? So we can't, because of the shapes around each of the atoms, we can't get this sheet to be completely flat. It sort of has this up and down motion to it, okay? But it's pretty well lined up chain for chain. okay? The purple here is supposed to represent all those different side chains. So we could have a valine coming off here, an isoleucine coming off here, okay? A bunch of different things can come off of that, but the backbone is what really matters. The backbone is going to form those hydrogen bonds and either make an alpha helix or a beta sheet. Back to the outline. Yeah, so we talked about hydrogen bonding. Ionic interactions with dipoles are important in the solubility of ionic compounds in polar solvents. We're going to talk way more about this in 2A3. Oops. Okay. So this is a simulation where we start out with a salt crystal. Right? This is a crystal lattice we talked about, the alternating positive and negative ions here. This is nice because it actually shows the motion. It's not like that crystal is stuck and it's not moving at all, right? There's always some motions of those atoms. We can add water. And the water starts to dissolve the salt. The thing I like about that this simulation is a lot of times when you look on YouTube or you find some video about how salt dissolves, it looks like the water has like evil intentions. Like a bunch of water molecules gang up and they're like, let's go get that ion. And they like scroll over there and they just grab it and they pull it away. It's like, no, they don't have a nervous system. They don't have any desires, right? They're just attracting, right? So what happens is the water comes up here. One water molecule cannot pull an ion off of this crystal. You do have to get multiple ions to pull that ion off of the crystal, because the ion-ion forces are actually stronger than the interaction of any individual water with that ion. But if I get multiple water molecules, we can form multiple attractions to the water molecules that can eventually pull the thing off of it. All right. If I freeze it, you can see by the orientation of the water molecules which ions are positive and which ions are negative.
Hydrogen.
For the water molecule, which side is the positive side? The hydrogen, right? The white ones. Because the oxygen's more electronegative. So if we look at this ion,
It's negative.
It's negative. It's positive.
It's positive.
this ion has to be positive, right? Because all the negative ends of the water molecules are sticking to it. This ion is negative because all the positive, all the white parts of the water molecule are attracted to it, right? But again, you see that you have to have multiple water molecules around each ion to keep that ion from then going back into the crystal. You just sit and watch this thing bounce around all day, right? Pretty cool. All right. This one I think is out of place, this learning objective. The student can qualitatively analyze data regarding real gases to identify deviations from ideal behavior. I don't even know why this is in this section. This belongs in 2A. We're going to talk about gases in 2A, and then we're going to talk about deviations from ideal behavior when we do the ideal gas law in 2A. It says no business being here. All right. Student is able to describe the relationship between structural features of polar molecules and the forces of attraction between the particles. Yes, you will have to do that. The student is able to apply Coulomb's law qualitatively to describe the interaction of ions and the attractions between ions and solvents to explain the factors that contribute to the solubility of ionic compounds. The student can apply Coulomb's law qualitatively. So they might ask you to do something like comparing which things have a higher solubility. For example, more likely to dissolve in water? Sodium chloride or rubidium iodide?
I'm mixing sodium chloride.
Sodium chloride, why?
Because
It's not as large.
It's not as large. So if sodium ions are interacting with water molecules, the water molecules can get fairly close to that positive charge. But if we're talking about rubidium ions, which are much bigger,
they're all mixed together.
the water is not going to really be able to get as close to that positive charge coming from the nucleus, right? So there's a weaker interaction here. So I would expect rubidium iodide to be less soluble than sodium chloride. What's the other factor that affects interactions with ions? The charge, right? So things with +2 and -2 charges you might expect to be more soluble as well. All right, a couple things from the big idea notes. Here's a nice picture of a dipole-induced dipole like we were talking about before. All right, here's a nonpolar molecule, maybe O2, that has a nice perfect distribution of electrons around it. But a water molecule's partial negative side comes in here, it's going to push those electrons away. It's going to induce a dipole in this molecule. This molecule doesn't want to be unevenly distributed because it doesn't have a nervous system. It normally would be perfectly evenly distributed, but the water is inducing that dipole in it. I might have to clean this up and move this around a little bit. I'm scrolling way down to the end. I think we talked about this a little bit. All the different types. So we're including dipole-induced dipole as an interaction now. Right? Here's the London dispersion. Here's dipole-dipole. Hydrogen bonding a little bit stronger still. But you could talk about ion-dipole interactions. That's what I'm trying to draw right here. An ion interacting with a polar molecule. We call that an ion-dipole interaction.
How is that different from ion-induced?
Ion-induced dipole would be like if I tried to take NaCl and dissolve it in oil. The oil molecule is some big long hydrocarbon that's nonpolar. There can form an interaction here because this ion can induce a little region of negative charge here, pull those electrons in this molecule close to it. This is supposed to be a molecule, not some, oh, looks like a turd or something. But it can induce a little dipole in this molecule, and so you can form an interaction here. But those interactions tend to be relatively weak, especially compared to ion-dipole interactions, okay? So they're saying between 3 and 15 kilojoules per mole is how strong this interaction is. Well, if we go up and we look at the strength of ionic interactions, those are 400 to 4,000 kilojoules per mole, right? So if these have a maximum of 15 kilojoules per mole, and we're trying to pull that ion off of some ionic crystal lattice, is one oil molecule going to be able to do it? Heck no. These are, even at the low end, 400 kilojoules per mole. These interactions here, 15 kilojoules per mole is not going to pull this thing away, right? Now when we go down, I guess you can sort of see it here, when we go down to the ion-dipole interaction, this is a much stronger interaction because this thing's already polar, right? So this could be between 40 and 600, so now we've got some overlap in the energy of their interactions. so much that if we get just a couple of water molecules, let's say these are each 100, well, if we get 4 water molecules around this ion, they can form a stronger interaction with that ion than the ion can form with its crystal lattice. That's why they're able to pull those things off. But it only happens when you have multiple water molecules causing multiple attractions. That's where you're going to get them pulled off. All right, that's the other thing I don't like about a lot of those videos you find online. A lot of times they'll show the ion like on the side, on the face of the crystal getting attacked, which is not really that likely because the ones on the face don't have enough space around them for the water molecules to get in there and pull it off. The ones on the corners and the edges, there's much more physical three-dimensional space where water molecules can get in there. Right? I put a link somewhere on here. Maybe I didn't, so I'll just YouTube it. How does the salt dissolve water? Okay. How water dissolves salt. So yeah, this is one of the bad ones, right? First thing that's bad about it is that the water is just like going like this. Why? It can go like this, which it does show, right? But it doesn't show that the water molecules are actually like moving and interacting with each other, right? It does show the salt moving, but see how they're ganging up? Let's get him! Let's pull him right out of there! Yeah, we got him. I don't like this one. And it's French. This one's much better. See those water molecules? Jiggling, vibrating. See the salt crystal vibrating? They're showing the interactions of this ion with the other ions. Right? It doesn't want to leave. It takes a lot of random jigglings and random movings around, but before the water molecules, enough of them orient themselves around that ion that they then can overcome the ion-ion interactions and pull that bad boy off. I don't know why they chose this background music. It should be like,
This is a love story.
Tool or something.
That was literally the video.
Well, that was literally the video,
It
but
was like 30 seconds.
It's like a
this
story.
is actually,
That thing song.
well, what they say here, this is like a simulation that was actually run on a computer. The other one is an animation, which is why it doesn't match reality. Somebody's like trying to draw the path of those things. This thing was calculating the path. So even though it's a very short video, it probably took a long time for a computer to actually make that video, because it had to do every calculation of every interaction of the thing that's in there. Which is also why it tried to simplify the output. See the water molecules in the background? No, you can't because I paused it. The water molecules in the background is just representing as little bars, because it's taking so much computing power to factor all these different interactions that it's saving computer power by making these things just like look like little sticks, I think. Or maybe it's just trying to focus you on the ones that are actually doing the attracting of the ions, which are the ones up there. Okay? Still my favorite video of salt dissolving in water. Maybe I'll do the remix with some little something, little wheezy, little cheesy, little oozy. Yeah. All right. Now, the properties. Oh, man, I forgot about this. Bunch of good pictures here. At the bottom here, showing some examples. So here's an ion-dipole interaction, right? An ion interacting with a polar molecule. Here's a hydrogen bond, water with methanol. Two totally different molecules, but the OH of methanol is interacting with the oxygen on water. Here's a dipole-dipole between two different polar molecules. Here's a dipole-induced dipole. This molecule always has a negative end over by the oxygen here. When it comes close to this hexane molecule, it induces a little positive right here and a little negative over there. Okay? Here's an ion-induced dipole, and on the bottom right, a dispersion, an induced dipole in both of those. Okay. What are the properties that they're going to ask us about? Does it tell us? Yes. 2B3. Boiling point. This is probably the best one. Because what does it mean to boil?
For a
Yeah.
molecule to
It has to overcome whatever attractions are keeping it in the liquid state. So the stronger the attractions, the higher temperature you're going to have to heat those things, the more motion they're going to have before they'll overcome those forces. Honestly, with the well, we're going to cut these two out. So really, I think most of these, vapor pressure is probably the hardest one. Vapor pressure is the only one that's inversely related to the strength of the forces. Because vapor pressure is saying if you have a liquid, it's asking, basically, it's a measure of how much of that liquid is turning into a gas. So actually, the weaker the forces, the more gas you're going to get coming off, the higher the vapor pressure is going to be. All right? Try the homework for Monday. I think you should be able to do it all. And do Monday.
Yeah. Anybody not hit it?
And then, is there a definitive quiz date?
Tuesday.
Wait, what
Well, I'm not
was
gonna
the
answer
Tuesday?
Quiz on Tuesday.
I actually called it yesterday.
Are you doing the election next
Said-
week? Are you doing the election next week?
Yeah, why not?
Oh, no, I have, shadow